what we're going to do here is to establish the need for something beyond a double integral, and then create a triple integral that will answer the question for us. The thing I want to look at is finding the mass of some solid if the density depends on x, y, z, and it has units like grams per cubic centimeter. Those don't have to be the units, but let's just use those so we have something to write down, is known. We can't find the mass of a 3D solid if the density is changing with a double integral. I mean, all the dimensions are already used up. So what am I supposed to do? Well, we want to take a chop, but the weird thing is, what we're going to do is we're just going to, on the inside of the solid, we are going to take just a little tiny box. What I want to do is find the volume of that box, which is going to be something like what? Delta x, delta y, delta z. If I'm measuring in centimeters, then the units of that would be centimeters cubed. I wanted the mass, so I'm going to have to multiply by the density, like that. This is going to be something like grams per cubic centimeter. We get the cancel, and you can see that what we're left with is grams. So what does this measure, right? This is going to be an estimate of the mass of that one little box that's just floating inside the solid. Now, it's not the exact mass, because we said basically this density was constant throughout that little box. Now in general, the smaller the box, the less that's a lie, because we're not giving the density enough time to change. But meanwhile, it's an estimate, probably a good one, of the mass of the little tiny box. But we don't want the mass of the little tiny box. We want the mass of the whole solid. So we stack them all up and add up all the masses of all the little tiny boxes, and what that's going to be is the mass estimate of a French fry. And then I stack up all the French fries next to each other, and that's going to give me a mass estimate of a potato slice, a fairly thick potato slice if they're French fries. And then I add up all the masses of all the potato slices, and what I should get is an estimate of the mass of this whole giant blobby potato. Now, like I say, the smaller delta x, delta y, delta z get, the better this estimate gets. And so we do the same exact thing that we did in Calc 1 and Calc 2. We take a limit. So I need a limit, but I need delta x needs to go to 0, delta y needs to go to 0, and delta z needs to go to 0. That'll make our estimate better every single time. And what we're going to get? Well, we can see that we're actually taking the limit of an integral, the limit of an integral of an integral of an integral. Right? And so we're going to get an integral, and then an integral, and then an integral. We're going to have the density function, which will be the integrand for our function. You can see that when we take the limits of all the deltas over here, those all turn into d's, like this. Now normally we like limits of integration, but we actually don't even know what the solid is. So what we usually do is call the solid something like S, and that actually will give us both the notation for a triple integral and the actual definition. The other notation you're going to see for triple integrals is very similar to what we had to do for polar and for double. You're still going to have the triple integral. Very often they'll just call this rho, or rho of xyz. Remember that delta x times delta y times delta z is a small volume. In other words, it's a change in volume from one slice to another. So instead of this, we could put dv. And you're going to see that quite often when they don't want to actually talk about the limits of integration. The s still has to be here because we were finding, after all, the mass of something. So that gives us what we're going to have to look at to calculate things like mass of a solid and not just volume.